Hello and welcome to another session of EPO 640 Electric Drive. So for this session, this will be the last part of DC Drive, and for this lecture we will be discussing on the open loop and closed loop system of the DC Drive. So in a simple open loop control, so you have your input, okay, V input, and then your output will be of course your load, okay. So for a simple open loop control, okay, it's easy to implement, and in some application it's good enough, okay, but speed is not automatically corrected, okay, as the machine when the machine is connected to the load, okay, and there will be no current control, and this creates problems when there will be a step change, okay, on the reference, okay. So in order to we will introduce the current control for the loop, okay, loop of the DC drive. So here you can see this is the open loop, okay. This will be the open loop, and this will be the closed loop system. So you have block G, okay. Block G represents the open loop gains of the controller, okay, or the system, and it's in a forward path, okay. And block H, okay, block H represents the gain of the sensor, the transducer, okay, or the measurement system in the feedback path, okay. So a different direction from the open loop gains, okay. So here you have the summing point. So summing point can be either add signals, okay, together, in which a plus symbol, okay, is used, showing the device to be a summer, okay, used for positive feedback, okay. Or it can subtract signals from each other, in which case minus symbol is used, showing that the device is a comparator, okay. So it's used for a negative feedback, okay. So here we have a comparator, okay. Example, okay. So the output of the system, okay, output, so you can see output, okay, output is G times the error, okay. And note that the error signal, okay, this error signal is also the input to the feed forward block of G, and the output from the summing point, okay, summing point equals to, okay, error equals to input minus H times the output, okay. So if H equals to 1, which is the unity feedback, okay, then the output from the summing point will be, okay, will be error equals to input minus output, okay. So eliminating the error term, so you have your output is equal to, okay, output equals to G input minus H times output. Okay, so therefore you get G times input equals to output plus G times H times output. Okay, so if you rearrange the this equation, okay, you rearrange it, okay, it will give you the closed loop transfer function of closed loop transfer function. Okay, so the output over input is G1 plus GH. Okay, so for a cascade control system, okay, so while the example just now, okay, is of a single input, okay, but single output closed loop system, the basic transfer function still applies to more complex multi-loop system. Okay, so here we have a multi-loop system, and most practical feedback circuits have some form of multiple loop control. And for a multi-loop configuration, the transfer function between a controlled, okay, and a manipulated variable depends on whether the other feedback control loops are open or closed. Okay, so here you have it's easy to look into as a cascade control structure. So for a cascade control structure, okay, it's flexible. Okay, so the outer loops can be added or removed depending on the control requirements, and the control variable of an inner loop, okay, for example the speed, okay, or the torque, can be limited by limiting its reference value. And the torque loop is the fastest, okay, so torque loop is the fastest, speed loop maybe the slower, and the position loop is the slowest to process. Okay, so in a subsystem, okay, you model the DC motor and load can also be modeled. Okay, so the assumed load is proportional to speed, okay, within this equation. So the DC motor has an inner loop due to the induced EMF, okay, due to magnetic coupling, okay, and this creates complexity in the current control loop design. Okay, so for example, we will try to model the plan of the current control system. So so to design the controller, so we need to know the transfer function of the motor and load, okay, and the transfer function of the power converter, and to let's say to get the subsystem transfer function, or we will try to compress the subsystem of the transfer function into the main function, okay, and to find the control parameters for the given performance. So the the current controller will look like this. Okay, so we will try to explain within the controller, the converter, the DC and motor load. Okay, so this will be the current controller that we will try to set an example. Okay, so you have your input, okay, IA, and the output will be the current. Okay, so current input and current output, and then you have your feedback system. Okay, so this will be the gain for the PI type controller. Okay, PI type, okay, proportional and integral type. Then you have your open loop gain function. Okay, and this is a open loop gain of the fourth order. Okay, so later on we will try to reduce it into the second order. So the first function will be the mechanical model. Okay, so you have your input torque, okay, on RS, and this will be the output will be speed. Okay, and since so from time factor, okay, time-based equation, we need to do it into a step-based function. Okay, why we need to change the time-based to step-based is because in order to process the order from using because we are using machine, so time-based is actually is difficult to process, okay, by the machine, so you need to transfer it into step-based. Okay, and so the transfer function will be okay, in step-based. Okay, so this will be the transfer function. And next we will look into the motor and load model. Okay, so same thing, from the time-based equation we need to transfer it into a step-based equation, and you have your transfer function, okay, here, and this will be the motor function, DC and motor and load function. Okay, so you have your input for torque, output will be speed, and you have on EG, okay, electromotive force, okay, and your VA will be the input also. So for a current controller, we can assemble. Okay, so you have your current PI controller, okay, your converter, and we put in the DC motor model here. Okay, so what's missing is the converter part. Okay, so for the converter, how we model the converter, so the converter can be modeled as a delay gain. Okay, both gain and delay. So you have VC as the input here, okay, in, out, okay, and okay, and also the PI controller here. So this is PI controller for power converter is this will be the function. Okay, so we rearrange in the current controller. Okay, so you have all the three main subsystem, okay, in the current controller. So now we want to rearrange the controller. So you have the basic you have your forward, okay, GS and HS. So the input and output. Okay, so for a current controller, input will be I*A. Okay, so this will be the output. Okay, so we will try to rearrange the current controller. Okay, in this way. Okay, so this can be further compressed, okay, into this. Okay, and you can see that we have managed to get IA as our output. Okay, and it can be further compressed. Okay, so you have this DCN motor load. Okay, can be shown in this gain. Okay, so this will be the mechanical motor constant. Okay, and you have this function. Okay, and for that we have the current controller, okay, function. Okay, so this will be the PI type current controller. You have your gain, okay, open loop gain here. So system is in the 4th order. Okay, so if you're designing without computers, you need to simplify. Okay, so simplification number 1. Okay, so TM is in order of 1 seconds. Okay, so hence you have your open loop gain function becomes this, and the system 0 cancels the controller pole at the origin. And also the relationship between the denominator time constants. Okay, so T2 is in the middle of TR and T1. So you can make a simplification number 2, make the controller time constant equals to T2. Okay, so then you get your open loop gain function will become this. Okay, again the controller 0 cancels one of the system poles. So after simplifications, the final open loop gain function will be this, and by now the system is now in the 2nd order. Okay, and from the closed loop transfer function, the closed loop characteristics equation is this, and when we expand it, it will become this. Okay, so design the controller by comparing system characteristics. Okay, so you get both of this equation. Okay, and if you simulate using a computer, okay, so you get for most of the value of sigma. Okay, so the higher value of sigma, you see that your control will be more stable. Okay, so if you want further readings, you can also check out this textbooks. Okay, so most of the reference that I've done here, okay, so I've this from the textbooks. Okay, so from model control engineering. Okay, and this power electronics converter. Okay, for that, thank you, and you can check out the exercises that will be posted. Okay, so for now, thank you and have a nice day.